the first thing I want to talk about, and some of this I kind of mentioned to you guys, but I'll start from scratch, is the different types of machine learning that we have. So there is supervised machine learning, and then there's unsupervised machine learning. And
is this actually machine learning, or is this just regression?
so regression is a form of machine learning. This is like the bigger family of machine learning. And then I'm going to talk about regression with gradient descent.
Okay.
But yeah, I'll get there. So that's actually going to next thing I'm going to show you. So what is regression? So regression is if we have something like the price of a house and the square footage of a house, and we're trying to compute if there's a relationship between the size of a house basically and the price, right? So we go ahead and we get a bunch of readings from recent sales of a house, and we find that a house that was 100 square feet was maybe $100,000, right? But then a house that was, 1,000 square feet was $150,000, and so on, right? And typically, this would make sense just from analyzing house prices. The bigger the house, the more it's going to cost. However, we know there's also other factors involved, such as the location, number of bedrooms, and other things that we call features. However, right now we're just trying to analyze one specific feature, which is the size of the house, and understand how that affects the price of it. So regression is one of the supervised machine learning methods that you can do to try to predict a continuous value. That's different than classification. So when you're looking at supervised machine learning, there's two main kinds. We have regression, which is this case, and then we have classification. Another name for classification is also logistic regression. The word logistic coming from logic, 1 or 0, true or false. But ultimately, they're both the same thing. In fact, this is more a binary classification because you're saying yes or no. But yeah, you could make it a ternary classification, yes, no, or like whatever the third option could be, maybe, I suppose. But typically, it's a binary thing. It's either you accept or you reject. So regression is going to be, again, where you have a square footage and a price, and you're trying to compute a prediction. So if I have a house that is this square footage right here, what can I predict the price is going to be? And so more than likely, what I can do is I can sort of draw a line to predict that. So I could draw a straight line to try to predict that. I could also try to do something quadratic. So I could create a curve. I could go ahead and do some really, really fancy formula to try to fit everything together. For example, maybe I should have done that before I went ahead and redrew it, but let's just draw it again. So if I have my math like this, I could usually use like trigonometry and create a cosine wave that hits every single spot of the test. However, that's really bad. That is what we call overfitting. Why is this overfitting? Because now, do you think that this weird line is really going to sort of be useful to predict an additional value? I mean, already we can see from our own eyes that either of these cases are going to be useful in trying to predict data. This is just all over the place. And this is kind of looking at the idiosyncrasies of the data, basically. So it's looking at the noise of the data and just trying to overfit it. So we want to find the middle ground between these. Maybe the straight line is not the best. I think here quadratic is good, but this is definitely overdoing it. Now, mathematically, how we can compute those? Well, I have the math over here for that. If we're doing a straight line, if you remember from high school math, a straight line is y equals mx plus b, right? Where m is your slope and b is your y-intercept. That's where the line hits the y-axis, right? And your slope is how diagonal this line is. Okay, so if I'm trying to compute a linear formula, that's all I need. I can, instead of using m, I'm going to use the keyword theta, or the symbol theta. So I could also rewrite this like this. theta 1 x1, and this is the same thing. However, these theta 0 is different than theta 1, so I'm just using the same different this notation for the same thing, right? And if I want to make this nicer mathematically, I can also do something like this. And then just say x0 is equal to 1, right? Because then that cancels out, and it just becomes a y. So this is like saying x0 and x1, but this is just 1, which gets eliminated, okay? So now if I want to do something quadratic, all I have to do is do something like this. Like that. Or actually, I could, technically, this can also be rewritten like this. Squared, like that. But x2 could be the same thing. Why? Because how can I generate more features from the same data? I could take the values here on this x-axis and just square them. So now I have not just the square footage, but the square footage squared. So if I have a feature down here, and this feature is just like, let's simplify this into just being simple numbers here. So this is like 10, 20, 30, and 40. If I want to generate a brand new feature, all I can do is I can say 10 squared, 20 squared, 30 squared, 40 squared. And now out of nowhere, I've generated a brand new feature that mathematically is very similar because it's just a squared. But by doing that, I can make a quadratic function and actually try to fit that using that. Now, if I go and keep doing this for n features, or sorry, for n training points or value points here, each of these are a point. If I do that, if I go to like, what is this, 1, 2, 3, 4, 5, 6. So if I have 6 items here, so I go squared, cubed, to the 4th, to the 5th, and to the 6th, that's how I'm going to end up with that sine wave, basically, okay? So, but that's skipping a little bit ahead. Let's go back to talking about supervised learning. So supervised learning, regression, we're trying to predict something that's continuous, right? So the more it grows, the more it goes, and we're trying to come up with a formula that we can plug in and get the value out of. An example of classification is going to be something like if we were looking at cancer. So suppose that we have 0, 1, that's binary, and then we have the following data.
Did you say cancer?
Yeah, cancer. We're trying to detect cancer in someone.
What's that?
Yeah, so suppose this is a tumor size. That's our feature. And then this is whether the cancer is malignant or what's the other word? Benevolent, right? So basically if you're gonna die or if you're gonna live kind of thing. Or if you need chemo or not, kind of, okay? So when it's malignant, that means the cancer has like entered the bloodstream and gone through the body, and that's when you're in trouble. But you can still live, don't get me wrong. People can survive cancer. So anyways, typically, looking at this data, what it's trying to say is the bigger the tumor size, it gets to the point where really big tumors pretty much indicate that the cancer has already gone malignant, okay? That's, of course, just looking at the data. But how can I actually separate the data and say, based on the tumor size, is there a specific threshold where I'm going to be like, yeah, okay, if your tumor is this big, you have cancer. And not just cancer, but you have a malignant tumor. And so you're trying to split the data into two. So you need to come up with a line or, and you get to higher dimensions, a plane or whatever, that splits the data. So in this case, I think that this is a nice little line that will split the data. Are there false positives? The idea of something that is like, it tells you that it's malignant, but it's not? Yes. This one here. Actually, this one's a false positive here. And this is a false negative. Right? Because our binary classification algorithm says anything on this side is not malignant, and anything on this side is malignant, right? And that's the line that we came up with from a machine learning algorithm. So it's saying, yeah, this guy doesn't have a malignant tumor, but he really does. But, you know, it's one case. For every other one, we're good. So that's 1, 2, 3, 4, 5 out of 6. So basically, 5 out of 6 times our thing works really nicely. 1 out of 6, we lie to the person. They don't know they actually have a malignant tumor, and you know they could have had help, but we didn't give them help because we thought they were good. So on the other hand, on this side here, for 1, 2, 3, 4, 5, 6, 7, you know, for 6 out of the 7, our algorithm says, yeah, if the size is bigger than this line, then it's a malignant tumor. And so we gotta get them checked out, start them in chemo or whatever. However, for this one guy, he's gonna be taking chemo when he didn't need to. He could just have the tumor removed. So that's gonna be a false positive, okay? Then these are truths, true positives, which means they are actually correct, and then these are true negatives. They form what's known as a confusion matrix. And true positive, true negative, false positive, false negative. Doesn't matter which way you put these, but ultimately, when you're trying to show somebody that your algorithm is really good or not, you need to put that. So that's something that we will put on a paper where we measure whether like something is good or not is based on this. Because like, if all your test data is of people that don't have cancer, and your algorithm just always says you don't have cancer, and you're like, yeah, it works great. Yeah, but is that really a representation of what it is? So if you're trying to do machine learning on text and trying to find mistakes, odds are there's very few mistakes on a page. So then your algorithm just assumes that there's never a mistake. Your accuracy is going to be really high, like 99%. But really, if you look at this closely, you're going to have a bunch of false negatives in there. And so this is an N, not an F. Can we really say that our algorithm is really good? Not really, because it's not detecting any of the errors. So this is a better measurement of whether something is effective or not. And then from there it goes to F-score and other things, which are just math done on these 4 values and so on. But anyways, back to this. You don't always have to stick to something like this in terms of one sort of feature. You can have multiple features for binary classification. Here's an example of that. So here we have tumor size, and then we have the age of the person. And you're still trying to linearly separate the data. So we might have something here like that, The algorithm, if you're just trying to linearly separate the data, it'll try to draw a line. And then in this case, we'll try to get the best fit. So you might still have something of what is it, a false positive or false negative, I'm not sure. But, it'll try to do its best case. However, you can go into higher dimensions to try to split the data into multiple groups. So you might actually come up with a math equation that's like an ellipsis to circle this. And then everything outside of it won't apply. So that's another thing that you can do. So I'll stop there talking about the introduction of supervised learning. And very quickly, let's talk about unsupervised learning. So unsupervised learning, you're not trying to either decide yes or no, or trying to predict a value based on other data. With unsupervised learning, it's more about discovery, data mining, trying to recognize patterns where you don't see them. So suppose that you have the following data here. Okay, I'm going to copy this twice before I draw on it. A very popular machine learning unsupervised algorithm is clustering, k-mean clustering and other things like that. Clustering tries to take data and form groups out of it. So in this case, the clustering algorithm may decide, if you decide, you got to tell it how many groups you want to try to make from the data. So you're like, I want to make 2 groups of the data. So I want to split the data into 2 pieces to try to discover something about the data. So the algorithm might draw a line right there and say, this is one cluster and this is another cluster of data. However, I might say split the data 3 ways. Well, then the algorithm might go ahead and draw something like this. And you can go on and make this n clusters for n items of the data, where each one will be individual clusters. What kind of uses could this have? Well, it's very useful in image processing, actually. If you're giving a picture of something, so let's say one of the pictures that we're working with, you can use clustering to detect different areas of the picture, like the sky will be one cluster, the foreground could be another cluster, people could be another cluster, trees could be another cluster. And people at Stanford went ahead and did this, and they actually converted a 2D image into a 3D image using clustering to be able to detect depth. So clustering could be useful in our case if we have a certain area of pixels that are not working well with the Polaroid filter, because then we can go ahead and apply this, group those pixels with a special category, and run a different algorithm on that. As for regression, in our specific case with the Polaroid images, what we're most likely going to do is get the new RGB values based on the previous ones. As for binary classification, what we're going to end up doing is, once we decide on a brand new picture we've generated, we will run into a binary classification algorithm to decide if it's acceptable or not, which is basically just a pass the quality standard. So all three types of machine learning can work together to solve the same problems. They don't have to be individual. But typically the way you run them is you do clustering first to learn more about your data, and then you decide if it's a yes or no thing, like stock market, buy or sell kind of thing, go with binary classification. If it's something where you're trying to predict something based on other data, but it's a continuous flow of data, then you're going to do regression. So regression means it's continuous. That's where the word regression comes from. Okay, so from there, I'm going to show you a little bit of notation, a little bit of how gradient descent works. But first, let me give you some data here. That while we're not really going to focus on the data, I want you to kind of get an idea of a couple of different things about machine learning based on this. So let me just write this real fast. Maybe one more line. And this is still recording, right? Yeah, okay, good. Okay, so here we have some data. And again, we're sticking with the square footage of a house. So that's the living area. But we're also adding number of bedrooms. So that's another feature. So each of these columns will be a feature. You can have as many features as you want. In fact, there's a limit. But typically, the more features you have, the more you know about the world and the better predictions you can make. So again, if you're trying to predict the cost of a house and all you know is the number of bedrooms, that's not really going to tell you much. Even knowing the area of the house, the size of the house, and the number of bedrooms won't tell you much. But if I gave you like 100 different columns and they all are each individual data, then you, as a realtor, could make a way better estimate of the price of the house. And that's really what they do. So ultimately, there's a limit though, because you are going to reach a point where there's going to be unnecessary features. Like, for example, I think they say whether you have a solar panel in your house doesn't affect the price of the house. So that would be a feature that would be useless. So that's not something I'm going to get into today, but there's algorithms to remove useless features that don't affect the outcome or the accuracy of your algorithm, okay? But for now, we're going to stick to these two features. So we will call them x1 and x2. And the next one's going to be the size. And x2 is going to be the number of bedrooms. So the way we're going to do this is we're going to create a hypothesis, which is going to be, again, the data notation that I was using earlier. And because we have two x's, then you could consider, it doesn't mean it's quadratic, but it does mean that you will have two different m's per se in it. So you will write this like this. Another way that you can write this to make more sense mathematically is you could do this. Which we like to call that our bias. So I'm just going to put an x0 so that way each theta has an x next to it, even though in every single case, x0 will just always be 1. So it's like a column full of 1s here that we're adding. Doesn't really tell us much, but it makes the math easier because now I can throw scary math terms at you and convert this into a summation. Okay, so let me tell you first what I did here. So let me actually put a little bit of notation here. So x here are your input variables, or features. That's another name for it. And then when we get to y, I'll just put it here for now. That's our output. same variables and features. And something like this, xy, is a training example. If I want to have the ith training example, so like this, so each of these are a training example. So this is the first one, the second one, the third one. So if I want to indicate a certain training example, I can write it like this. So like the second training example will be x2. So that's not exponential. That's just a notation to indicate that. And so another one is when you see m, that's a number of training examples. And here I'm using n, but that is not the same as the m here, because the n here is going to be the number of features. So I'll put that here, I suppose. So think about this from a math perspective. I'm trying to compute 400, and I have two numbers. I have 2104, and I have 3. What I'm trying to do is, and this is the part where I can go far away from this, actually. I want to point to it. But what I'm trying to do is get a value here. So this value right here, this h of x here, for the first example, I want this to be 400. Okay? I want that to be 400. And I have 2104, and I have 3. So mathematically, if I wrote the following equation, I said 400 is equal to 2104 times some value x plus, or sorry, not about x there, theta, plus 3, theta 2, plus theta 0. Could you solve that? Could you come up with some numbers? And there's a lot of solutions to this, but could you come up with some numbers that could give me that? I can give you one off the top of my head very fast. I can say, make theta 1 equal to 0, make theta 2 equal to 0, and then make theta 0 equal to 400. That could work, right? Because it would be 2104 times 0 plus 3 times 0 plus 400.
That's to approximate the other one.
That's the next part, right? Okay, so that would work if that was if our machine was trying to predict always only one specific scenario, then I could just, that's like hard coding the answer, basically. But here's the thing. Now I have more than just one case. I have 3 cases here, and I could list a couple more, but imagine how much more. So here's the issue. The theta that I come up with there are not going to work for the next one, right? Because if I just do 400 there, in the next case, I'm going to get 400 when I should have gotten 232. So I'm trying to use math to figure out what numbers I can put there that apply not just to one case, but to all cases. Now that's a harder problem, right? Like I can't come off the top of my head. I mean, well, let's see, it might be like theta could be divided by like 1/10, and then 3 could be, I think I'm just going to put 0 there to make my life easy. And then the theta 0, I don't know, like 50 or something, and that would kind of give me some numbers, right? But what I'm going to show you is a method of actually systematically coming up with the solution, obviously. That's the machine learning part, right? We are trying to figure out what values of theta do we need to put there that will work for all cases. Is there always going to be a clean solution, like one final solution? No, because like there may not be a special number. So we're just trying to get to the one that's the closest, right? So how do we define what's closest? Well, that's what we know as the least square error. So that's the next thing that I'm going to show you, actually. Yeah, I'll come back to the summation part. So again, the thetas are our parameters. And we have our hypothesis, which is what we're trying to figure out, right? That's like our y, per se. In fact, we can say that given this hypothesis minus what the correct value is, we want this difference to be small, right? So this is our predicted value, and this is our like actual value, right? So this is, once we plug in some theta that we come up with randomly, we're going to get some numbers out of that. That's this guy. This, however, is that column. What we know, the final column, right? So backing up a little bit, when you're doing machine learning, what you want to do is you want to take data that you know the answer to. And you're going to use that to teach the computer so that when it sees new data, it can use what it learned to predict the new data. But if you don't have data to train it with, then it has no idea. So like, suppose you're trying to predict the weather. You're going to give it like 10 years of weather information. It knows, it starts to find a pattern in the weather. Then tomorrow you're like, okay, based on those previous 10 years, what do you think is going to happen tomorrow? That's because it's already learned 10 years of data. If you just tell the computer, yesterday was raining, what do you think is going to happen tomorrow? Well, then all it knows is that it rains. So it's going to be like, well, I think it's going to rain, because that's all I know. But if you told it like, well, on January it rains a lot, February it rains a little bit, and then the other months is dry, then it's going to be like, well, historically it hasn't rained in February, so I think it's not going to rain, right? So it needs to be trained on data. And so that's why we have the price of a house for a bunch of houses, which we will train it with, and then we will try to predict and compare it to what it should be, and then ideally try to make them even so that when it sees new data, which it doesn't know the answer to, it can make a more accurate prediction, okay? So we're going to take the value that we predict, and we're going to subtract the actual value. And we want to make this difference really small. But because that difference could be positive or negative, we're going to square that difference. We're going to square it. And now it's a positive number always, right? Because negative number squared, positive. So this is known as the least square. And we want to minimize this value for all cases, right? Not just for the first example or the second example or the third example, for all of them. We want to add them together and then try to make that as low. And what's going to end up happening when you do the machine learning is every time you run it, it's going to, that difference is going to start going down. But eventually, it's going to sort of slow down, and they may never reach zero because, again, it's never going to be perfect. But you will be the one to decide, okay, this is as close as I can get. Because sometimes it's just going to stop, actually. But you probably want to stop it before so it doesn't run for a long, long time. So backing up to the summation notation here, what we're trying to compute with the machine learning is we're trying to run from I equals 0 to n. So for all the parameters that we have, so I0, theta 0, x0, theta 1, x1, theta 2, x2, we're trying to sum them all together. So we're converting this into this. That's the same line. We're just making summation here. However, a better way of writing that, and this is getting into linear algebra, is using the transpose. So this is known as transpose, and that is taking the inner product between two vectors. And what that means is when you got a matrix, you do a diagonal flip on the matrix, and that's how you get that. So if you don't know that, then you can review linear algebra. But that's okay because ultimately you don't code this. You just use the algorithm. But that's where that comes from. So why using linear algebra is because it's very easy to multiply an entire column against an entire column, for example, which is because you're dealing with a lot of data instead of trying to do everything on each individual value. So linear algebra and machine learning are one, basically. They go hand in hand. So, okay, so we have this x squared, and we're trying to minimize that. So we're trying to minimize this data here. And so we can go ahead and rewrite this as follows. We can say that h theta xi for the ith example minus the actual solution for the ith example squared. And we're going to sum all those together. And we want to find the minimum of that. And we just throw a 1/2 in there because it makes the math easier. So just accept that. So because ultimately this is for only one training example, right? But we need to add all the errors together. So when we compute our error for the first one, so we gotta to compute the error. Where's the table? We're gonna multiply this times our theta 1, multiply this times theta 2, add theta 0, and then whatever that number is, we're gonna subtract 400 from that. We're gonna save that somewhere. Then we're gonna do the same thing with the second line, and we're gonna save that somewhere. And then we're gonna add them all together, and that's how we're gonna get the total minimum. So that's gonna give me the entire error for all of them together. And this is what we're trying to minimize. So we call this, or just one of the names is j of theta. And our goal is to minimize j of theta, because that means we found the best value of the thetas, okay? So, to better understand why we're trying to minimize this, a good example for this is, I'm gonna try to draw this, but I don't know how this will go. We have two features, right? Because we have two features and one y, that's like thinking x, y, z, where this is the y. Well, it would be x1, x2, y. But if we're trying to graph that, one way of thinking about it is that's x, that's y, and that's z, right? So it's a plane. It's no longer, it's three-dimensional space. And this could go n dimensionals, technically. So I want you to think of this hilly sort of plane. It's going to look like a video game. Kind of like a video game map. Let me add some color to this. The colors is the elevation. Are we on time? All right, we're half in. Okay. Oh, maybe not there. Okay, so red is really high, and then yellow is like semi-high, and green is like low, and blue is really, really low. Okay? So what we're trying to do is, this is our data. And when we start, like, what do I pick as theta 0, theta 1, and theta 2? I gotta pick something as a start. And it turns out that the best thing you can do is just pick something at random. So when you pick something at random, you're basically picking a spot in the map here. So let's say we picked that right there. And so what we want to do is we're gonna guess some numbers, so whatever the theta is, and then we're gonna try to change those numbers to reach our minimum of our summation. So what's gonna happen is we're gonna take steps towards wherever is downhill. So in this case, it could go like this. And eventually, when we get to the lowest point of the map, that's the lowest error, and that's what we're trying to achieve. However, in this case, that's the lowest point of the map. But suppose that the other random spot we picked to start was here. In that case, we take always the step that takes us lower. We would have ended up here. These are known as local minima, and this is our optimal or global minima. This is the theta values that would have given us the best value ever. Like, this is like the most accurate solution. However, this one is also good, but from here, we can't get here. So this is the problem with what I'm going to show you, which is gradient descent. The best way to explain it without math and whatnot is actually something I saw on Wikipedia. So imagine you're in a hill, and it's really foggy, and it's late in the afternoon, and you're trying to get out of this mountain. It's a really top hill, or I guess mountain, not hill. You're in a mountain, and you're trying to get out of the mountain. And it's really, really foggy, so you can't see more than like a step ahead. So what do? Well, your logic says, I'm trying to get off a mountain, so I should go downhill, right? So you look around where you're standing, and you're like, okay, if I look ahead of me, the ground goes up. If I look this way, the ground goes up. If I look this way, the ground goes down. If I look this way, the ground goes down. Obviously, that way is uphill. I'm trying to get out of the mountain, so I'm going to go downhill. So you're like, well, I could go this way, I could go this way. Well, okay, which one's steeper? Is this more downhill than that? So like if the ground is like maybe 30 degrees down here and here it's like 60 degrees, it means that this is steeper. So like this must be the way to get out of the mountain. So you always pick the steepest descent. So you take a step that way. When you take that step, now you can see another area because you move through the fog. So then you do the same thing again. You look around and you see, okay, from here, where do I go where it's steepest down? And that's basically what you keep doing. You keep doing that, and ideally, you keep going down wherever you can, and you will hopefully end up at the lowest possible spot. What's going to end up happening is you're going to go down, and you're going to get to a spot where you're probably going to be like flat. And like everything around you is flat or higher than where you want to go. So like you reach a ditch, basically. That's where you stop. Because at that point, going uphill is counterproductive because you're trying to reach the best case. Now, in the mountain, you may reach a lake, but you may also get out of the mountain. But you don't know, because it's going to depend on when you start, right? So that's one of the problems with machine learning is, and what gradient descent is that you're trying to find the local optima, but it may not be the best solution. But you can't see that, because you can't see the entire area. You can only see what's ahead of you. Now let me add more complication to this.
You may never reach
The best solution.
Yeah.
You will reach a good solution, but it may not be the best one. So like this one here is a good solution, you know. The error is pretty small, but this one's even better. But you may never reach that based on what you started. So there's nothing you can do about that. There's a lot of algorithms to try to pick what you can do to try to avoid this, but there's no clean solution that I can just tell you like, yeah, this is the way. It depends on your data.
If you go the entire place, go up or go down, switch the entire place.
Well, yeah, but that's doing like
Brute force.
huge amount of computation. Yeah, brute force basically. Like, okay, let me just try picking random values of theta and see which works better. So that's bad because it's going to take forever, right? Furthermore is this. Okay, every line that you see here is a step, okay? But suppose in my example, every time that you walk and you measure the height, like I don't know about you, but like unless it's like a huge difference in like steepness, like this versus this, like it's all going to feel the same downhill to me, right? So I suppose I have this like nice little machine, like a little, well, not a machine, but like a little thing that gives you a ball, you know, the elevation tool that I can put on the ground, and then I can figure out the degrees of inclination of that slope, and then I can go here and check out the degrees of inclination, and I can do that 360 around me to find the real like lowest inclination, right? That takes time. That's computation time. If I do that every single step I take, it's going to take me like an hour to do 100 steps. And if the mountain is really big, by then it's nightfall, and then I get killed by the cold weather or something. So sometimes I have to make a decision. I'm going to measure the ground, and then instead of measuring every single step, I'm going to measure every 100 steps. And that's still going to get me hopefully to my goal, but not as accurately, but maybe quicker, I hope, right? Because what's going to happen if you take bigger steps? Well, if we look at our line here, you know, you start going this way, and then you may go this way, and then you may go this way, and you'll get to the right spot. But over here, you may start going this way, and then you go this way, and then suppose here it's uphill, right? Right here it's uphill. But if you don't measure until you get here, then you might actually get to the minimum, right? So it could go both ways, good or bad. You could also end up here going like, okay, you're like, okay, this is lower here. But then from here, you instead of taking tiny little steps this way, you take such a big step that you actually end up over here. So the amount of steps you take and how many times you do them and how separate they are may lead you to the wrong spot, but at the advantage of getting there faster. So when we talk about the learning rate, or when you hear that in like a tutorial online about the learning rate, that's how big of a step you take. Tiny steps, a lot of computation. Bigger steps, less computation, but you may overshoot your goals. So it's a balance that you usually set by hand on what you want to do with that. So, yes.
I guess it also depends on your resources, right?
Well, yeah, computational resources, yeah, which is basically like how long it takes for you to measure that step, which is basically how long it takes for you to compute all the training examples and recalculate your weights, which is basically the algorithm. So gradient descent, it is spelled like this. Basically, repeatedly take a step in the right direction, which means the direction of steepest descent. That is where you're minimizing your error. So your error is going down the most if you do that number. Okay? The way we write that is like this. So I'll go term by term. So this term means update the parameters data. So all the data at 1, 0, 2, 4, 5, all the variables that we have to compute a number for, a real number. We update those. And the colon equals, if you were here earlier for the class, that's what I was talking about. So in math, if you see this, That's equality. You are making an assertion. You're saying A and B are equal. If you see this in math, you're saying algorithmically, take this value and assign it to A. So that's like in C++, this will be equal, equal. This is assignment and operation in C++. So this is very different than this. This is saying you're asserting A and A are equal, whereas here you're saying take the old value of A, maybe add something to it, and then put it back on A. Okay, so that's just some basic notation stuff. Over here, so you're taking the old value of all your thetas, and you're going to subtract the partial derivative with respect to theta I of j theta. So I'll write that here. Since this is the partial derivative with respect, not of, but to theta I of j theta. And then this is your, I guess I shouldn't point to the alpha, I should point to that. That's your partial derivative. The alpha here, that's alpha. That's how big of a step you take. The smaller the number, the smaller the step. If you make it 1, that's a big step you're taking. Think about the math here. You're recomputing your thetas, and you're trying to find a better theta. And if your better theta says it's smaller than your current theta, so like suppose your theta is 5 here, and you recompute and you say, well, I think we have to subtract 1 from that. So like this becomes 1 here. So if you did that and your learning rate was 1, this theta from 5 would go down to 4. But if your learning rate here is like 0.01, then you're going to multiply that 1 times 0.01, and now from this, instead of going from 5 to 4, it's going to go to like 4.99, right? So it's a smaller change. So that's your smaller step. So this controls that. So this is like, yo, you got to decrease this by a lot. And this is like, yeah, we're going to censor that, and we're going to decrease it by a lot less than what you think. Okay? So that's where the alpha comes from. And you pick that. A good alpha to pick, 0.03, 0.05, something like that. A bad alpha to pick, anything bigger than 1 is way too big. But again, the smaller the alpha, the more computations you gotta get. Because like imagine that like the solution to this was that 5 had to become a 3. If your alpha was 1 and this worked nicely, maybe the first time it'll go from 5 to 4 and then from 4 to 3 and then you'll be good. But if you pick an alpha like 0.01, you're gonna have to do 200 of these calculations to get that two values down, right? And
that's the thing that you set manually?
Yeah, you set it manually. And so here's the thing. Suppose you pick an alpha of like 5. You're gonna way overshoot this, right? You're gonna go from 5 to 0 when the answer was 3. That's the other bad case scenario. So, yeah. So this is something on on all the libraries, Python libraries and whatnot. This is a number that you actually set manually. I mean, you can go with the default, but you can fiddle with that. If your algorithm is taking a long time to finish, the word is converge, then you want to increase that alpha. If you think you can do better, like if your algorithm is like finishing in like 5 minutes and you're like, I wonder if I can do better, you can try to make that smaller and see if you get a higher like accuracy with a quicker, even if it adds, instead of 5 minutes, 10 minutes, because that's still pretty fast. Okay, so this is where things get a little bit nasty because we're talking partial derivatives. So I'm going to simplify the problem, and I'm going to assume that we only have one training example. And I'm going to take you to the derivation for one example, and then we'll extend this into end examples, okay? So let me rewrite this. So this is the partial derivative with respect to theta of I, which in this case will just be one case, one example. So we only have one training example, which means one pair of x and y's. So we have, in this case, we have x1, x2, and y. So that's what I'm talking about. So we need to work out that partial derivative. So how good are we with derivatives here? Like, do we know, for example, like, I don't want to use x, but like, suppose we have a squared, what's the derivative of that? 2a. Yeah, so basically you take the exponent and you bring it down, and then you subtract 1 from the exponent. So it becomes 2 minus 1, which becomes 1, and then the 2 goes there, okay? So suppose that we had, so like this one, which is more like what we're looking at. Just A, right? Because the 2's cancel each other out. All right, good. So we know some basic stuff. All right, let's make it harder. Everybody know what the chain rule is. So the chain rule says, here, let me write it because I actually wrote it down here to make sure. So suppose we were doing this, okay? So the way the chain rule works is you take the derivative of the outside, and then you take the derivative of the inside, and you multiply it times that. So what this means is we're going to take the derivative, so we're going to consider this to be like an a to the 8th, and we're going to do the derivative of that, which is going to be 8a7, and we're going to multiply that times the derivative of the inside. So whatever that is, which in this case is 3x4 times 2x2. So that would be 3 times 1/4 x3. Oh, sorry, not 1/4, but 4, which is 12. Yeah, you're right. Minus 4x. Good. Yeah, that is easy, right? Once you remember what the rules are. So yeah, that's basically what happens here. So this ends up being, in this case, 8 3x4. So you're taking the derivative of the outside first, right? And then you multiply times we figure out in there, which was 12x cubed minus 4x, like that. And you can leave it like that. You could simplify it. I did an extra simplification where I took a 32x from the other term. So this became 3x cubed minus 1. But you could leave it like that, right? So I factor out a 32x from this term. Don't worry. That just forget about that. Just as long as you know how to do that, we're good. Okay, that's what we care about. Okay, so what we need to do is we need to take the partial derivative of that. So what's that going to be? You guys, here, let me copy that. Bring the 2 down, which cancels out with the 1/2. That's why I put it there, to make my life easy. And then it just becomes h theta x minus y times the partial derivative of the inside of this, right? So that's that derivative. Okay, so what's that derivative going to be? Okay, well, what does this mean, actually? What does this notation mean? Well, remember, all that was our thetas added together. So like theta 0, x0 plus theta 1, x1 plus blah, 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 until theta n, xn minus y. Okay? That's all that means. That's earlier, that's what I said, and I just put it in that format. So we're really taking so I even wrote here, we take the partial derivative of this sum with respect to the parameter theta I, but all terms in the sum, except for one, do not depend on theta. Okay? So the only term that is going to depend on this theta I here is going to be theta I xi. Every other term is a constant. And what happens when you take the derivative of a constant? So what happens when I do something like, yeah, exactly, like 5. Then this just gets canceled out, and this becomes 4x, right? So all of these are basically going to be just constants that are going to be eliminated. And the only thing that's going to remain is the theta I. So it turns out that that nasty thing is just going to be the top part. So the first part, h theta x minus y times. And so like I said, all the other terms are constants. So this is literally a plus like c, a bunch of c's. It goes away. And what's the derivative of this with respect to theta I? So this is like saying 5x. What's the derivative of 5x? 5. So this just becomes xi. Okay? So this gives us what is known as our learning rule. Okay? So this is our learning rule. So we can go ahead and update this formula. And just plug in what we solved. And again, this is your alpha. So I had a thing out here explaining how it was alpha. We already talked about that. So we just did this derivation for one term. Doing this for like multiple terms, which means multiple training sets, that would take hours. So instead, I'm just going to be like, do it at home. You know, that's what they say. Yeah, I'll do it at home and give you what the solution will be, the general solution, okay? So you're going to repeat this until convergence using the following steps. So this is going to be the good one. Oh, it's a J, not an I. Let me move this so it fits. It'll make some sense though when you see it. It's a J, not an I as well. Okay, so all the things on the top are J's and the things on the bottom are I's. So what is this formula? This formula is as if we took the derivation of all the training examples. And as you can see, it looks similar to the one that we had above for the single training example. So this was for one training example. That was the derivation. And this is for M training examples. As you can see, it's almost the same thing with the exception that there's a summation going on. Okay, so this should make sense just, even if you don't trust the derivation, it should make sense just because they look very similar and you're just adding together, right? So you can verify that for yourself if you want, that this summation is indeed the partial derivative with respect to theta I of j theta. And remember, this whole thing is j theta, where if you use the original definition for j theta when you have M training examples. Okay. So it turns out that for the specific problem of linear regression, which is what we're doing, or also known as ordinary least squares, which is the minimization of that square function that we had, which is what we're doing, the function of j theta does not actually look like the previous graph that I showed you. It actually looks more like a spoon. So, which is good for us because it makes the problem a lot easier. That did not turn out as I expected. There we go. Can you see that three-dimensionally? Maybe if I get rid of that line. Well, it looks weird. I think we should leave that. It's a spoon, okay? It's like, it's that. What's the good thing about that? It doesn't matter what spot I randomly pick. I'm always going to end up at the global minimum. So unlike the other one, which is like hilly and there's like multiple local minimas, there's one global minima here always. So whenever you're doing linear gradient descent, it's always going to converge on the global minima, which is good for us, which is going to give us the right solution every single time, the best solution every single time, if we're doing it linearly. A better way of looking at this is a top view of that plane.
Wait, but isn't this just the squaring of the hill?
What's that?
If you take the hill and turn it into equation, if you just square it, wouldn't you get that?
No, not really, because if you square it, it's just going to make the hills hillier.
So you would remove all the negatives. It will keep it more.
No, not quite. It'd be nice if it could, but no, it wouldn't work like that. I know what you're trying to say, but no. So, yeah, so we can take advantage of this because it's a property of the ordinary least square regression, that it's always going to look like this if you're doing it linearly, okay? Now, that doesn't mean that we're going to get the perfect answer to our machine learning and it's going to work forever. I'm just saying that this specific algorithm, we don't have to worry about local optimas, local minimas when we, well, by the way, optima and minima, same thing. Optima means optimal. Minima means minimum. Both interchangeable for what I'm trying to say, which is the deepest spot. It doesn't matter where we start, because either way, we're going to end up at the minimum. Also, a good example here is the number of steps you take. If you take like really big steps, you'll actually do something like weird like this, but you'll still end up here. So with ordinary least squares, As long as your step is not that big, then you'll be okay. So basically, it always will have, it's called a bow shape. It will also have a NOS bow shape and global minima with no local minimas. As you approach the local minimum, the gradient becomes smaller and smaller, so the steps also become smaller. So even if you start with big steps, those steps will become smaller as you get there. And when it converges, you have found the least square fit to the data, which means this spot right here, which means that the error doesn't become smaller. It remains the same. That means you found your best solution, okay? So this is known as batch machine learning. Now let's talk about quickly, and we have 10 minutes, so I think we'll be fine. There's online learning and offline learning. What is the difference? With offline learning, you run through all of your training examples, and then you update your weights. With offline learning, you update your training example, you update your weights after each individual training example. So that's, if I looked at the first line of my input data, my training data, I try to compute a data based on that. Then I look at the next line and I try to recompute data that way. And you might initially be like, that's really gonna be bad. And yes, it will take a little bit longer to converge, but it's gonna be faster. It's gonna take more computations, but it's gonna be faster sometimes, depending on how big your data is. If you have a really, really big data set with like 1 million training examples, and you're also constantly getting even more training data, your best bet is to do online learning because it'll actually finish faster than if you try to update the weights with 1 million points, because that's a lot of computations you gotta do to update the weights just once. You can also do batches, so you can do like 10 at a time and so on. So the summary of this is just so you know when you see algorithms. If they say online learning, they're updating after each training point. If you see offline learning or also batch learning, they're updating after X amount of training is given, points is given in. So when you're doing online learning, the name of that is actually called, and I have a hard time pronouncing this word, so I'm gonna write it. Stochastic. What's that?
Didn't someone say?
No, I don't know. I don't think so. Maybe. Good question for another time. So yeah, stochastic gradient descent is online learning. And so basically when you're doing batch learning is too much, then you can just do it like this. I'll write the pseudocode for this real fast. J equals 1 to m, training examples. So for each training example, I need more space. So you're basically re-updating the weights every single time after each of them. Perform an update on all parameters for all I, and the indexes in your parameter vector. So basically, I wrote here a joke saying just adapt, bro, because you're basically adapting it after each one. Alternatively, so I'm going to skip a lot of linear algebra, but it turns out that with gradient descent, there's actually a formula that you can run and you can get the minimum automatically without doing machine learning. And however, there's a catch. And there's a big derivation you can do with linear algebra to get here and derivations, where like x theta is basically a matrix where you have all your training examples. Except all the training examples, but not the y. Oh, this looks like it turned off. Okay, there we go. And then you multiply this times theta. And then you got your y, which are all your training examples for that as well. That's why it's matrices. So if you have a matrix like that and you got a matrix like that, what you can do to find out the minimum is take the transpose of this, which is flipped diagonally, and then multiply that times the regular matrix, and then find the inverse of that matrix, and then multiply it times the transpose again, times the vector of your y's. The catch here is this. getting the inverse of a matrix. By the way, the inverse of a matrix is when you multiply a matrix as its inverse, you're going to get a special matrix which is called identity matrix, yes, which is basically a bunch of ones like this and then zeros everywhere else. So you're trying to find out this matrix times something will give you the identity matrix, and that's your inverse. The problem is, if you take a linear algebra class, they'll tell you that you can't always find an inverse to a matrix because it just doesn't work, like depending on the dimensions and other things. So the moral of the story is, yes, this equation would automatically solve our ideal thetas, but most of the time, you're not going to be able to do it because of the inverse. So just an aside there on that. But yeah, so ultimately, to summarize the lecture, the biggest thing is this. This formula right here is your gradient descent. And if you do this enough times, you will converge on those minimums. And how you do that is, you multiply, so you pick, so this is now actually what happens internally with the values that we got. You pick random thetas in the beginning, you multiply them times what they should be, you subtract that from what the actual value should be. So for example, I'll just come up with numbers here. So square foot, maybe 100 square feet times 3 bedrooms should give you $200,000 or something, okay? So what you're gonna do is you pick some random numbers here for theta 0, or sorry, theta 0 is technically here, plus theta 1, and then 3 times theta 2, okay? And this is your y. So you pick some random number for this, some random number for this, and some random number for this. And then you subtract, you multiply that together, you find out what that is. So say you pick 1 for each of these. So you get 1 plus 100 plus 3, so you get 104. And you subtract that from 200. And that's going to give you 96, right? You multiply that times the same values here, all the x's, so 103. So that would be 103 would be, I don't know, whatever that is equal to. And then you multiply that times your learning rate. Oh, wait, you add all of these together for each of them. And then you multiply it times your learning rate. And then you subtract that from your current weights. And that's how you get your new weights. And then you do this in a big loop until the error decreases, or until you can stop. If you want to try just 100 steps, and you can do that. And then it'll converge. So that is linear regression with stochastic gradient descent. Of course, we spent a lot of time deriving this because I want to show you the math, because ideally what you end up doing in the computer is when you call Python, you're going to give it your training matrix, which is basically all your features. You're going to give it your y. So you're going to give it your x's. It's going to ask for your x's and your y. So now you know your x's are going to be your features and your y's are going to be your predicted output. You're going to give it that. You're going to give it a learning rate. You're going to run it. And then it's going to give you back your thetas, your weights. And then you will basically have your formula ready to go. So if you want to test a new number, you just feed the thetas times the features, and you're going to get a y. And that's going to be your predicted y. So that's it. That is linear regression. And so neural networks, by the way, since we got like 2 minutes, is just stacking a bunch of linear regressions on top of each other, or logistic regression as well. So for different features, you feed different things, and you go through different levels, and you end up with a final thing, and there's activation functions, blah, blah, blah. Neural networks, deep learning, all it is the same thing here, but you do it multiple times on the same data. That's all it is. Everything else is magic, and they want to scare you. It's true. Things like support vector machines, yeah, they're a little bit different. But it's all ultimately the same thing. Machine learning is this. And everything else is just cherries on top of this, but it's still the same thing. So it's all math based, basically. So yeah, hopefully you guys got something out of that.